Welcome back to the classroom. My name is Mr. Wong and today we're covering Module 8, Applying Chemical Ideas. Inquiry Question 2, Analysis of Organic Substances. And we are going to just do a quick recap on what we've talked about with proton and carbon-13 NMR. Textbook reference, same as the last two lessons. So with the idea of NMR comes due to a concept called magnetic spin. Now, all charged particles have a quantum mechanic property known as spin. That doesn't necessarily mean it's spinning, but it's the ability for a charged particle to generate its own magnetic field. And then once you have a magnetic field similar to two bar magnets, it can interact with another magnetic field. This concept of spin can also happen for atomic nuclei. So what we mean by atomic nuclei, it's the atomic nucleus of an atom, so the protons and neutrons added together. And in order to have spin for atomic nuclei, you need to have either odd number of atomic mass or a odd number of atomic numbers. So in this case, the ones that we use, carbon-13 has the odd atomic number, or atomic mass, while as hydrogen-1 has the odd atomic number. Okay, so that's the idea that we have here. So you can think of the charged particle spinning, and as it spins, any charged particle that spins, it's able to generate magnetic fields. Now, usually on its own, the charged particle, I'll say that again. So under normal conditions, when there's no external magnetic field placed onto these particles, the magnetic spin of the hydrogen-1 or the carbon-13 nuclei are randomly orientated, so they can be in all different directions. So as you can see here, some are down, some are cross diagonal. However, once you put an external magnetic field, the nuclei will begin to align with the field. So in this diagram that we have here, you can see the magnetic field is the direction of the magnetic field is directly up. And then you can see that the charges are either aligned parallel with the field in that direction, or it's aligned parallel against the direction. Okay, and it's this point where some nuclei can be going with or against. That's the interaction we're going to try and harness to identify particular structures of organic substances. Okay, so if you can actually look at this chart here, you can see with a magnet alignment, you can see it's a measure of energy. So obviously up here we have high energy, down here you have low energy. Let's say, for example, our magnetic field is aligned our external magnetic field is aligned from north to south. So the magnetic fields are coming down this way. Now, what will happen is if I have my magnet, and this is north, this is south, so this is aligned with the direction of the magnetic field, or in a way it's going against the magnetic field, so north attracted to south. This is a low energy state. So if this is the usual attraction that we see, it represents low energy. If we generate a magnet that can go north and south orientation to our north pole here and our south pole down there, as this is not usually favored because it's a repulsion, that means there must have been a lot of energy that was put into this state to make it uphold this orientation. Now, to transition from here to here, you'll need to use a little bit of energy. Okay, so that's what we said here. If it aligns with the field, the nuclei is in a low energy state. If it aligns against the field, it's at a high energy state there. Now, the way we can move or transition the low energy to high energy, so from here all the way up here, we need to use radio waves. Okay, so the radio waves just so happens to have enough energy to cause the nuclei to flip and favor the high energy state there. The absorption of the radio waves with the interaction of these magnetic fields will produce really sharp spectral lines that correlate a specific type of nuclei. So it could be, for this case, hydrogen or carbon, and it could specify the type of environment the nuclei is in. Okay, so that's what we have. We're trying to use radio waves to work out the various types of nuclei involved. As you can see, radio waves have a big range of frequencies, so that's why we're able to do that. In terms of NMR, the magnetic field strength that we use will affect the results. Later, what we call chemical shift we take into account, and also it will tell us the chemical environment of the nucleus, which we'll also talk about very shortly. So let's start with a chemical environment. So a chemical environment refers to the bonds surrounding the adjacent atoms. We're looking at the connectivity and the relative position this particular nuclei has within the molecule. So let's use the example of propanol 1 and propanol 2. Say I am trying to look at the carbon environment. Okay, so I'm trying to look at the carbon environment here. This carbon is bonded to an adjacent hydrogen, oxygen, and hydrogen there. So that's the environment it has here. If I use this carbon here, you can see, oh, I forgot that carbon there, but the second carbon we have here is bonded to a hydrogen, bonded to a hydrogen, bonded to one carbon, bonded to two carbons. So if we look at how it's bonding with the adjacent atoms, this carbon here is much different from our carbon on the left here. If I go then to this third carbon here, you can see again the adjacent atoms it's bonded with is much different from this carbon here or this carbon here. So in total we have 1, 2, 3 carbon environments according to this. Whereas if we go propanol, propanol, we can see that we have 2 environments that are exactly the same, or 1 environment, or 2 carbons that share the exact same environment, and then we have a center carbon here which has its own unique environment. So what does this tell you? So it actually tells you if we're using H NMR, we can actually work out specific bonds of where the hydrogens will be to the carbon, potentially. But also it can tell us the difference if we're dealing with isomers. So we can tell the structure, so structure of isomers can be identified. So that's kind of the beauty of using NMR here. One of the things that can affect our measurements is obviously chemical shift. Now, one of the examples is called electron shielding. Now we know that inside the atom we have our proton, and obviously that's the thing that will absorb the radiation and it's going to shift. Now outside the nucleus we have electrons, and if the electron was, so to say, blocking the absorption of radio waves, so the electrons absorb the radio waves itself, then there's nothing going into our proton here. So this going here doesn't occur. You might also need more energy, to cause the flip to occur. Once the absorption does occur, you can see that we will cause the spin of the proton to reverse, like so. Okay, We also call this shielding and de-shielding. So if we're essentially shielding or using negative nuclei, then we increase, or we will force the increased amount of radio waves that need to be absorbed. If you have a look at the charts that we have here, the absorption shifts go upfield, so the shifting that we see will obviously in that sense go down. And then if it's a de-shielding effect, the absorption shifts go downfield, so like so. So it can actually tell us the way the electrons are behaving in the molecular structure. The other thing we also know is electronegative nuclei withdraw electrons, so it causes de-shielding. So let's say, for example, with propanol 1, the oxygen here is a highly electronegative atom, so it's going to draw in electrons towards it, and that's going to cause shielding for the oxygen. So our oxygen here will be shielded here. Slightly different will be our hydrogens and carbons that are bonded adjacent to it. That's going to go through a de-shielding effect. As the electrons are being pulled away, they experience de-shielding. But what you can actually see here, as those carbons go further and further away from this oxygen, that shielding effect gets gradually smaller and smaller. And so that's also why we see such vast ranges of chemical shifts depending on the types of bonds and interactions of the molecule available. Okay, so there's that. Now, the whole point of looking through the structure is obviously to, easily distinguish the type of bonds we're dealing with. Now, we do need to use a reference point just because the variations in magnetic fields and shielding can cause a little bit of issue of working out what the sample is. So we use a standard sample called TMS. Okay, so tetrathiamethylsilanate, and it's used to compare these chemical shifts. Now, the reason why we use the structure here is if you actually have a look, the carbons all belong to the same environment. So they all have the same bond. So we're only dealing with one carbon environment bond. The silicon carbon bond is also very stable. So it should give us some nice reference values. So that's why we use TMS for these analysis. All right, so let's look at how to interpret the H NMR spectra. So firstly, in terms of the number of peaks, that will tell us the type, how many proton environments that we have here. So we have this proton environment here, and this proton environment here. Okay, so that's the two peaks that we see here. So that one, sorry. So this hydrogen here, I might just label that. So we have this hydrogen here, that's one environment. And then these three hydrogens belong to the same environment here. So that's why we have two peaks. We can also use the little mini peaks, the little shift splits, to tell us how many carbons there are within, or hydrogens there are in the same environment. So say for this split that we have here, we have 1, 2, 3 peaks. That represents that we're going to have 3 hydrogens within this one environment. So that is for this one here. We have 2 little peaks here. So that represents this one here. And then we have 1 peak to represent this shift that we have here. Okay. Obviously, the peak will tell us in terms of the absorption. So that gives us some really nice information there. Okay. So obviously hydrogen 1 will have a magnetic spin. We can use this to investigate the different hydrogen environments. Okay, so we already talked about this before in terms of the information that can be provided. I'll just leave this on for a little bit if you want to have a quick read and refresh. But you'll actually see each type of hydrogen environment will correspond to a particular chemical shift measured in parts per million. What you can also see here is the splitting patterns. So what we talked about, the splitting effect, intensity of the signals, that's what we see here. So depending on the amount of splits that we see, that would represent how many hydrogens potentially there are in the adjacent atoms. Okay, so this calls the signal splitting effect. So the number of peaks provides information of the hydrogen 1 bonded to an adjacent carbon. So if we have no adjacent carbons to the one that we're looking at, we only see one single peak. If we have one adjacent hydrogen in the adjacent carbon to the hydrogen we're looking at, then we'll see duplets. If we have two coupled hydrogens in the adjacent carbon to where our hydrogen is, we'll see triplets. And then if we see three coupled hydrogens to the adjacent carbon of our hydrogen, we'll see quartets. Now there is a little rule that we use, so we say the number of peaks will equal to the number of adjacent hydrogen plus 1. So if we have one peak, all right, so that obviously that just represents that one there, just the one hydrogen there. If we have two peaks, that represents the one peak of the hydrogen we're looking at, and also there being one additional hydrogen on an adjacent carbon. Okay, so this only applies to the hydrogen attached to the carbon atoms. Splitting won't occur if it's a hydroxyl group. So these are all the different kind of types that you will see. So the pattern we see is called the N+1 peak rule. That's what we call it. And you can sort of see the difference in the peaks. So if we get the two peaks here, right, that represents that there must be an adjacent hydrogen to the hydrogen that we have in the adjacent carbons. So you can always use this as reference in terms of analyzing the graphs here. If we have a look at this example down here, if we have a quartet, so we are assuming that we have three adjacent hydrogens to the hydrogen we're looking at. So that's what we have here. Whereas for this one here, you only have two. So what the two peaks represent is in our environment that we have with this hydrogen B here, there is only one hydrogen that's attached to the adjacent carbon that these HB hydrogens are at, and call those duplets. Okay, now where are the benefits of using the hydrogen NMR? Well, if you actually compare the two esters, you'll actually see that infrared spectra won't be helpful in differentiating between the two because they have the same functional groups, so that's not going to be useful. We have mass spectra, and but that wouldn't be useful too because it's the exact same structure, so the molecular mass would be the same. The carbon-13 spectra probably wouldn't help either because they have the exact same type of carbon environment. But if we use the proton analysis, we can actually see there are differences in terms of the environments here. We can see that over here for methyl ethanoate, there are two hydrogen environments. So the two environments that we see here is this one here. So this one environment, or we'll just circle like that. That's the one environment. Okay. And where's the other one? Oh, and then this is our second environment, sorry. So that's our second environment bonded to a carbon. Our first environment is bonded to an oxygen. So that's one, that's two. Okay, with our next one, we can see that we have one environment here we have this environment here, and then we have this environment unique to it as well. So it can give us a final idea of what the structure would be. This would usually be the final one we analyze when it comes to all the different spectras. Okay, so let's have a look at this past paper question. We have a molecule of C4H9Cl, and we get this one giant peak here. If we look at the four choices, which one would be the most appropriate in telling us the different type of structure? You have a think. If we actually have a look, the most correct answer would obviously be this one here. So if you actually have a look at the hydrogens, if I just draw them back, we have 3 hydrogens bonded to the 1 carbon, and that's for each one here. So each hydrogen is experiencing the same environment. So they're bonded to a carbon, and their adjacent bond is the same carbon bond here. So A would be the answer for this one here. All right, if we look at ethanol, we can sort of see the peaks that will relate to the level of shielding. So these hydrogens here have less shielding effect, so they are being less deshielded, so the relative peaks are lower, whilst the hydrogens here, more shielding at this end, so you can see sort of slightly higher there. All right, and then we go to the carbon-13. So exact same idea. You can use the values from the data sheet that will tell you the different structures. Remember, this is given to you in your nested data sheet, so all you need to do is reference the graph and then reference this chart to help you indicate the structure of your particular atom. So what I want you to consider here is we have this molecular structure, C4H6O2. What's the most appropriate structure based on this peak? Pause it here if you want to have a go. If not, please follow on after this. Okay, so let's go through this component here. So we can see in this particular environment, the peaks are relatively high, which would suggest that there was a bit of deshielding that we have here. We have 2 peaks, which represent there are 2 carbons in this particular environment. So if we look at this chart from 120 to 140, whichever one matches, so 120, it could be this one here, or obviously it could be one of these two, but we firstly don't have nitrogen, so that's not possible. And this is a benzene ring, which needs 6 carbons, which would represent, that wouldn't fit either with our structure here. So that means the structure we have here is the carbon-carbon double bond. So we need to put that in at some point. Next one we can have a look at is this peak here. So that's between 160 to 180. So the only one that really matches is this one here. So it represents we either have an ester here or an alcohol group. So we have R, C, that. And then the last one we have here, do in red, it's from 40 to 60. So from 40 to 60, we can see that it could be this group here, or it can be this group that we have going here. So obviously work it out from there. So let's try and draw it out. It's different structure. So we have our RCO, and then actually, so what we have is, so we know we have an ester group on our hands here, and then potential alkyl group that's over here. So we'll just leave that for now and we'll just continue on. So we're expecting to have 2 carbon-carbon bonds I'm going to draw them here. Obviously, because they are they are de-shielded, so you expect them to be relatively close to this oxygen atom here. And we've predicted the ester group, this bit here, because this says from 50 to 90, and obviously this is already over 50, which discounts this one that we have here. So we have that. Now, obviously, we are missing a carbon, so logistically speaking, we would expect that our last carbon would be carbon here. As you can see, it's not possible for the carbon to be on this side, or neither the double bond to be on this side of the carbon. So this is, logistically speaking, the best way of sorting it out. And then lastly, we have to add in the hydrogens. So it says we need 6 in total. And 6 is how many we have. We have 2 oxygens and we have 4 carbons. So that's how you solve for that one. Obviously, you don't usually just do this as it is with carbon. You should reference it with the hydrogen nuclear magnetic resonance spectra. So that's what you should look into as well. We will go through some more examples in another video, but this is just to give you a bit of comfort for it. And obviously, thank you to the guys at Rose Bay for supplying this question that I can use to explain. So there we have that. Okay, so that concludes what we need to talk about with NMR. So hopefully this gives everyone a little bit more context of how to use the chart to interpret the spectra and the structure. So yeah, hopefully you found this video useful, and you know, in the near future, hopefully I'll do a little bit more examples on analyzing these different spectra types. But until next time, you know, stay safe, and hopefully you keep enjoying chemistry.